Hello everyone, and thank you for attending today's webinar, Advanced EBSD Data Processing, Selection, Validation, Quantification. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer all these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck is available in the resource widget, which looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier or via EDAX.com. Now I'd like to introduce the presenter for today's webinar, Dr. René Decloux. René has been working as an application specialist for EBSD and later also EDS at the EDAX European Support Office in Tilburg, the Netherlands, since 2001. His focus is on instrument demonstrations, conference and workshop presentations, and after-sales customer support. This includes on-site training courses, assistance with analytical problems, and scientific collaborations. Although focused on Europe, his work has brought him to customers and conferences all over the world. The international travel is a great bonus for his hobby, geocaching, where he tries logging at least one cache in every city visited. As he has always been fascinated by the physical world around him, René has chosen to study geology at Utrecht University with specialization in materials science from a geological perspective. René's first introduction to electron microscopy and microanalysis came during his undergraduate thesis on deformation and pressure indicators in natural fault rocks from New Zealand, which involved a significant amount of SEM and TEM work. Later during his PhD thesis on nanometer scale melt structures in upper mantle rocks, he also learned about high-resolution TEM imaging and EDS analysis. Around this time, he also started using EBSD on the system without any automation. René's background in geology gives him a slightly different view on materials research, which has proven invaluable over the years at EDAX. In geology, one must often look at a material without any prior knowledge on how it was formed. Applying this view to man-made materials can be a great help in explaining unexpected test results or materials failures that customers need to understand. Now over to René.
Thank you very much, Jonathan. Welcome everybody to my webinar today on advanced EBSD data processing. And just the layout of my webinar today, I'll just start with a brief introduction. Then I will show you what the analysis software looks like, some of the basic analysis, how to start, one-button tools that we have in there. And then I'll go a little bit deeper, how to customize analysis that you can do, a partitioning of your data sets, exactly what data you want to work with. You can select exactly what you want. Then data optimization, we'll get there. I'll explain exactly what I mean. Feature correlation. And in the end of the webinar, I will spend a little bit more time on two new features that we have in the software. One is the parent grain reconstruction, and the other one is OIM matrix, which is based on reconstructed EBSD patterns and dictionary indexing. So let's start with a quick introduction why we want to do this. Now, normally when people are going to look for an EBSD system or they talk about it, people tend to focus on data collection specifications. So what type of detector do you have? How big is it? How fast can it go? Is it sensitive, etc.? And of course, those are really important parameters. But in the end, that's not what it's about. So let me just highlight the hardware that we offer really quick. So our main detector series nowadays, the Velocity Pro Plus Super low noise CMOS detectors, can go extremely fast, up to 4,500 points per second. Then we have the DigiView that is still out there. It's extremely flexible. We can mount it on almost anything. So if you have an SCM that is slightly non-conventional, for example, ultra-high vacuum system, or with a port that may not be ideal, in most cases we will be able to fit an EBSD detector to that. And of course, our Clarity direct detector that doesn't use a phosphor screen anymore, and instead uses a direct electron sense capture on the front on the chip, which allows you to go to really low current applications. But that's not really what I want to focus on today. So the real purpose of EBSD, of using EBSD, is a little bit pushed to the background if you focus on the hardware. So at the end of the day, what you need to do is understand your material. So you need to get good microstructural data, quantitative, that allows you to investigate any analytical problems that you may have. And to do that, you will need really advanced data analysis tools. So what we feel is really important for that is your choice, of course, full map, so full area analysis, or subset selection. Then we need to identify what points to trust. So the system can easily give some numbers, how to know what is valid. And if you have poor data points, is there anything still you can do with that? Can you improve that? Can you still get valuable data out of those points? And then, of course, once you have set up your analysis, you know what you want to do. And if you have repetitive analysis, you can automate that with templates, which gives us really high flexibility and also interactive analysis when you need to. Okay, now for all this analysis, we use a special program. It's called OIM, and OIM stands for Orientation Imaging Microscopy. And just to illustrate that here, so what kind of things you can do? Of course, you can generate maps, color-coded maps, grayscale maps, different layers on top of each other. And almost everything we can show in maps, we can quantify in charts. Then additionally, we can make what we call discrete plots. So plots where all the individual measurements are shown either as a pole figure or an Euler plot or perhaps an inverse pole figure. And in most of the cases, also these we can quantify with texture calculations. And this is what it looks like. So here we have the total user interface. I just opened a data set to illustrate the different features. And most of the functions that we need are directly available from these toolbars. So there's a number of toolbars that you can position around your screen any way you like. And the analysis itself is focused around the project tree we have here on the left. And I'll go into a little bit more detail of that in a moment. Then here on the right, in the main area of the software, we have all the results that we can display. So you have some text windows, mapping, charts, plots, etc. And most of those also have secondary view panes. So once you have a map, the default view is a legend, but there's much more behind it. So there's definitely worth investigating what's there, like interactive analysis or flexi view, where you can display wireframe drawing, pole figures, reconstructed or real EBSD patterns by just moving your mouse over your sample or over the data set, sorry. Now, maybe one of the most powerful parts of the software is here on the left in the project, that everything we do is organized by partition or subset. So let's take a look at that in a bit more detail. We have a project, and you can see that this project is built up of different levels. First, we have the project. That's the file that you're going to save in the end, and everything underneath will be contained in that project. Then we have these black icons. These are data sets. So whatever you have collected on your acquisition system, that's what you see here. And I often describe those as buckets with my measurements. That's where the measurements are. Everything else is just a description or a definition, but all the data is always in that data set. Then we have partitions. Those are these red icons. And partitions are effectively subsets. And a partition can contain a filter that defines which points to take from the bucket with all my measurements. So all the data that is underneath a partition only uses the points that you allow in that subset. And that can be maps, so different types of maps, as you can see here, EBSD, orientation maps, or chemical maps. They can be charts, like a grain size chart. Can be texture calculations. And because you can define these inside these partitions or subsets, you can make multiple versions of those with different parameters. So you can very easily compare different results by playing with parameters in the calculations. And then underneath a texture, you can have the quantified orientation figures like an ODF, an IPF, or pole figures. And then finally, if you want to compare data from different partitions, you cannot do that inside a partition because that only uses the data that is part of that particular subset. You can do that really at the top level of the project. We call this a multi-chart. And in there, you can compare data from different sources in your project. So that is a really important structure in the software that we use all the time. Now, once you have opened the data set, you have generated a partition, or the software has done it automatically based on the phases that you have, you can start with some of the basic maps and plots. And these are the most important ones are just specified here as predefined maps. So this is an image quality map. Go next to it, there's an IPF map. I can look for charts. These are all just single-click displays that you can generate very quickly. Now, if this is not what you're looking for, if you want a little bit more, you can do a contextual menu. So everywhere in the software where you want to make a change, where you want to optimize or modify something, is just right-click and select what you want to do. So in this case, I'm going to make an image quality map in grayscale. I'm going to add a color-coded inverse pole figure map, and there you go. So it's just right-click, and you can make whatever you need. And when this is something that you need to do more often, if you have some repetitive analysis to, for example, investigate a whole sequence of measurements from a production process, or maybe some experimental sequence, you can just prepare the definitions that you need once, and these custom definitions you can then save as templates. But, and remember the structure of the project tree, you can also copy them between the data sets, because the analysis definitions, the maps, plots, charts, or the partitions they don't contain data. They only contain a filter what to use from the dataset bucket, which means that once you have made them once, you can just copy them and paste them into other partitions and other data sets. And then you can generate all the analysis you need with exactly the same definition, which means that you only need to define your maps and boundaries, etc., just once. And then you can store that in templates, and you can store templates for all the individual displays like maps, plots, charts, textures. And here I just have an example map with a few grain boundaries indicated. But you can also do that for an entire analysis. So you can specify an analysis for a multi-phase material, here a duplex steel with a sigma phase, and then you have a partition for each of the phases. In each partition you specify what you want to measure, and you save that as a template, so you can just use that over and over again. And that allows also allows you to use a batch processing. So if you have this whole sequence, you do this once, you save a template, you run the batch processor, and a whole set of data sets will be processed and analyzed by the same definition. And it allows you also to save all the images, all the data, any legends. So it's not just the pictures. Also, all the quantitative data that is behind the generation of the pictures is always available as text files if you need to do your own calculations. So about these templates, you may have noticed that some of these buttons up here are grayed out. And that's where we can put our own templates. And if that's not enough, we have a pull-down menu where you have a long list of templates that we can apply. A number of those based on textures have been predefined. Others you can just make yourself and add to it. And these gray buttons up here, you can populate that. So with the next analysis, it's just a single click to generate the analysis that you need. And as I just mentioned, we can do a batch processing. You specify the template, as you can see here. You specify what you want to export as text files, as images, maybe something you want to do to the data set with cleaning or rotation, and then everything further is automatic. Now, an example why you may want to do that is a grain size analysis. One of the typical things of an EBSD map, especially if you have something that you can display in color coding like this one, then the color coding is based on the data in the active data set. So here I have a few different maps of similar material collected at a different magnification, and I tell the software, okay, make me a grain size map, and the scaling in each of these maps goes from blue, where it's minimal, and red, where it's maximal. And in this case, it almost appears that the image on the left gives you a larger average grain size. But of course, we have to be a bit honest here. I didn't put a scale bar on. So if I put a scale bar on, you can see that the maximum grain size here is only about 3 micron. And here it's over 10 micron. And that means if you have multiple data sets, you want to compare the data, what you need to do is fix the scale. And in this case, I have set the scale from 0 to 11 micron. So now all my maps are shown in the same color coding. And now you can really see an honest comparison between these maps. So that's something to be aware of if you do EBSD analysis. You're looking at a colors coding. The color coding is typically based on whatever you have in your display from minimum to maximum. And if you do that between different data sets, you can have quite a variation. And once you have defined this, you can make this into a template. You can put that into the toolbar so it's available by a single mouse click. So you just have a consistent map or chart all the time. Now, just to dive a little bit deeper into the subsets or partitions, this is a dialog when you right-click on the partition and look at the properties. And here you can specify which points and which grains you want to use in your analysis. So there are a number of parameters that you can select based on pixel parameters, based on grain parameters, and you can combine those. So in this example, I have made a partition formula or a partition filter where I'm looking for a grain size with a certain definition. In this case, a tolerance angle of 5 degrees, which is the default in the system. And then grains have to be smaller than 2.5 micron. And the phase has to be, in this case, alpha titanium. So when I have a filter like that in my partition, that's the only part of the data set that I'm going to use. So then I can make a map, I can make a pole figure, I can make a grain size chart only using those points. When I have that, I can also just modify it, in this case, just flip this smaller than, make it into a larger than symbol. So I see the big grains, and again, I can do the analysis of that. So it's very flexible in how to select points and grains that you want to work with. And just to illustrate that, here is a duplex steel. So I have mostly an austenitic matrix, but there is some ferrite in there as well. And when we do a mapping, the software automatically indexes the patterns as either austenite or ferrite. And that will already give you this phase map. So nothing you need to do about that. But once you have this open in the software, you can separate them. So here on the left, I have my austenite fraction. Here on the right, I have my ferrite fraction. And you can then also look at the grain size for each phase. So here, this is for everything. Then here on the right, I've made a multi-chart where you can see the austenite and all data. It's almost the same because there's so few ferrite available, but the ferrite grain structure on average is a little bit smaller than 1 micron, where the austenite is about 10 micron. So you can quite easily tell those apart. The other thing you can do, once you have separated different parts of the microstructure, in this case the austenite and the ferrite, you can look at the interface between those components. So here it's just showing the interface between austenite and ferrite, showing the phase transformation relationship, which is typically around 45 degrees. But you can also do this between any subset that you can make. Now, some cases it can be difficult to manually define in a fixed filter what you want to do. Then you can also do a custom selection. So here I have a partially recrystallized steel. You can recognize the recrystallized grains quite nicely here with nice uniform colors and deformed areas in between and also down here, for example. Then we can make a chart looking at the grain orientation spread. So how much deformation do we have inside each of the grains that is specified? And we can quantify that in a chart. Now, in this chart, we can recognize that there is some kind of cutoff at about ½ degree orientation spread. Over that, it's almost horizontal, this deformation, this distribution to about 10 degrees. But below it, there's a big spike of points from grains that have very little deformation. And when I just select those, so I can just select a fraction, that allows me to interactively split the data set into 2 components that I can then analyze separately. So here I have just an IQ map on both sides with a color coding of the selected fraction. And for example, for both fractions, I can calculate a texture just to see how this microstructure evolved. And sometimes even that is not possible. Then you can do an interactive selection directly on the map itself. So the image that I have here is an EBSD map on eutectic gold silicon die attach for power transistor application. So it's a silicon substrate with a gold coating on top. You can see some topography. Here in the middle, we have the IPF map. We can see the color coding very nicely. And here on the right, in a Prius image, we have a very strong indication of orientation contrast. So we can recognize the big grains. We can recognize the small feather structure of the small grains. And I would like to separate those. Now, I've tried to do this from a chart. That didn't really work. I didn't really get the grains that I wanted. So instead, I can just manually click in the grains that I want to select. In this case, I just wanted the really big ones. And then I can use that to tell them apart. So just pull the data set apart, make different partitions, and then in each partition I can make a chart like this one. This is grain boundary misorientation distribution. And here we have a lot of low angle boundaries, and here are a few high angle boundaries. And when you go to the larger grains, obviously we have much less interface length available, so also fewer boundaries. But if I scale that chart, you can see that the distribution really is identical. So in this case, there doesn't seem to be a real misorientation, microstructural difference between the very small grains, the very big grains. Probably if we go to a lower magnification, these bigger grains are their own feather structure. So this partitioning gives you a lot of possibilities to look at specific fractions of your data set. And we can even use that when we store all the EBSD patterns as well. So we can then just select certain parts of the data set to optimize indexing. So for example, we can extract diffraction patterns at every point. This is this flexi view I was talking about before. We have a pole figure, a pattern, a reconstructed pattern, orientation, representation in a wireframe. You can just move your mouse over the data set, and this is just dynamic. Wherever your mouse is pointing, you can see the result. And when you click somewhere, you can extract that pattern, modify background processing, modify the phase, etc. So you can really maximize the indexing performance. Especially when you have multiple phases, you can take the phases apart, and for each phase you can calculate its own background. And that can be especially useful when you have a very light material like an aluminium alloy with very heavy intermetallic phases like perhaps tin. When you then have an overall background for both phases, then you may get oversaturation of the tin patterns. And when you really maximize or optimize the image processing for both phases separately, you can get good indexing everywhere. On top of that, we have NPAR, and NPAR allows you to take like a moving average over your data set. For each pattern, we take a look at the ring of patterns around it on our hexagonal scanning grid. We average those 7 patterns together, and then we index that pattern. And that really improves the signal-to-noise ratio, allowing successful analysis of materials that produce very poor patterns. And just to illustrate that view, so here we can pull out this window. You can adjust phases. You can say use this phase or not. You can change the reflector table if you want to. You can modify the band detection with all the parameters that we have available for the Hough transform. You can do the image processing. You can switch on NPAR. You can do all kinds of other image processing, even advanced. You can make your own recipe of how you want to process patterns to really maximize the band detection. And then you can index by point, by subset, complete data set any way you like. You can, of course, combine that with chemical information. So here you can just select, based on an element or multiple elements, which points you want to assign to a certain phase. If they may not be distinguishable by EBSD alone, you can use the chemistry. And you can even do that in batches. So take a whole sequence of partitions for re-indexing or re-indexing with chemistry. So it's very, very powerful tool to help you to maximize the indexing performance of the system. And just to illustrate what that looks like, here I have a staple, very fine step size, small beam current. So you get a bit noisy map, you get bad indexing along grain boundaries. When I go for NPAR on that, the signal to noise ratio improves dramatically. You can see all the small structures here that were just lost in the noise in this one. And also the indexing improves from about, what is it here, 80% to maybe 99%. Another benefit of this NPAR optimization that we can do afterwards is that you can average the background when it changes with surface orientation. So you can use it, for example, for topographic samples like fracture surfaces. Here I have an example of a fib cut with horrible curtaining due to some artifact at the top. And normally, of course, we don't see anything in these curtains. It's just shadowed and there's no signal coming out. And when we apply npar to that, you can get a full indexing result. And you can truly see why they call it curtaining. So you can just see the bending of the surface everywhere. Now, of course, there may still be points that we cannot index, even after everything we've tried to do. And some of that is just misindexing, overlapping patterns that we cannot help. There may be phases that we've missed that we cannot index correctly. And of course, your sample can be porous. Now, how do we specify which points to trust? And for that, I want to quickly go to the indexing algorithm, what we call triplet voting, because that is what tells us not only what the orientation is that we can extract from a pattern, it also tells us if there's more than one possibility for an indexing solution. So we can put a measure on how sure we are that we have a unique solution. And we do that by specifying triangles or triplets. And for each triplet, we can identify an orientation, in some cases more. So here I've got 3 orientations for this triangle. Here's only 1, etc. And in the end, we have a table with all the possible orientations. And for each orientation, we have a number of triangles or triplets that match it. Then we do a very democratic way. We just count the votes for each solution, and the solution with the highest number of triplet wins. But that's not where it ends, because each triplet has its own orientation solution with it. So that means if we show that in an inverse Pohl figure, you get a little cluster of points of orientations that belong to orientation number 3, and the final orientation that we save is the average of those. And that makes it extremely sensitive to a very good orientation precision, even if some of the bands may be slightly misidentified. It doesn't really matter. Then the cloud just gets bigger, but the average stays in that point. And to illustrate that, this is a piece of this deformed steel that I just showed. I make here a profile through one of the grains with some substructure. And you can see here that the point-to-point orientation changes are typically well below 0.2 degrees, and some spikes over that, and those are really the low angle boundaries. So the orientation precision that we measure here at about 2500 points per second is between 0.1 and maybe 0.3 degrees. And that really follows out of this triplet voting. Now, another benefit is, as I just mentioned, we know when there is a second possibility that's as good. And when you would just use a fit or an angle parameter, it will not help you there, because if you have 2 solutions that are very similar, they will have the same fit parameter. So you cannot tell them, okay, this one's better than that one. But it also won't tell you typically that they are very similar, so you don't know if it's reliable. So what we do here, we know for each different orientation how many votes we have, and we can just look at the difference. So the number of votes for the best minus the number of votes for the second best solution divided by the maximum it could have got. And in this case, it's 0.6. And the CI, or confidence index value, in our experience, in most cases, when the best solution has 10% more votes than the second best solution, it's okay. So that means that the confidence index threshold of 0.1. And that is something we use all the time to remove suspicious results, or, as I will show in a moment, how to identify porosity. Now, first of all, here I have a zinc aluminium alloy, try to index that, and let's see how we can use the EBSD patterns to improve it. And what I have here, I just use a CI filter. I only show the good ones, it's about 75%, but then I flip that. So now I'm only showing the bad points. I take a pattern, I optimize the image processing, the indexing for those patterns that refuse to index in the first place, and I'm only going to change those. I'm not going to touch the points that properly indexed in the first place. And when I do that here on the left, you see the result. Now the result is almost 97%. So it's more than 22% improved over the initial indexing. And actually, there was a secondary phase in there that I also had missed initially. So saving the patterns and doing this offline really allows you to maximize the analysis results. Now, here's another one with a missed phase. This is an iron silicide sample. I've got 6 phases already used for indexing. And again, after indexing, I noticed there are a few grains that look okay and are completely speckled. So that indexing went totally wrong. I could identify those by the confidence index. And in this case, also chemistry. So I pulled these out, look at the patterns, optimize that, and identify what it is. In this case, it was a titanium iron silicide phase. I know what it is, then I can just re-index those points, nothing else. And then I can fold that back into the original data set. So now I've got a 7-phase map. That's one thing. Another thing, and this one is even more pronounced. When I look at this map, it's a nickel alloy with some tungsten, molybdenum, titanium intermetallics. And initially, these just looked like pores or dirt, perhaps, because there was just no signal coming out of them. But when we take those points, get a pattern, well, if you look there from a distance, you may be able to see a few bands, but you might think that's wishful thinking. But if I really optimize those patterns, we can still get this out. And now you can clearly identify the bands, the different zone axes, and that is very indexable. So again, I re-index those points and I add them into the data set. So we can use chemistry for that. So you can take the chemical information to differentiate phases, as I've shown before with the austenite. We can optimize the indexing of multiple phases where some patterns may be very different. And I always use it when I have a material with lots of phases, because when I try to index every pattern with everything, that may be difficult. So here I have an example of, again, this iron silicide material with lots of phases in it. Actually, in this area, we've got 8 phases, and I use the chemistry to get a good indexing result. But there are sometimes problems with that. And here, I really like to illustrate that with a nickel alloy with a carbide. The interaction volume for EDS is much larger than for EBSD. So that means that the signal coming from those small particles is bigger than the particles themselves. So if I zoom in here on the right, you see a chromium map where I just highlighted all the boundaries. And when I zoom into that, you can see that the chemical information is larger than the grain. When I just index everything as nickel in this case, I can get the grain size, but that doesn't match the chemistry. So if I use the chemistry to assign another phase to it, you can see I get a ring of misidentified points around the particles because the size of the chemistry interaction volume is so much bigger. What we can do then is we can use the indexing result to average the chemical signal by grain. And when you do that, you get a very sharp chemical shift or chemical change between the particle and the grains around them. And that allows you to get a very sharp phase discrimination and orientation discrimination at particles, even when they may be smaller than 1 micron, which is often shown as a, let's say, an average interaction volume for EDS. Now, then porosity. You can do a lot of stuff there as well. So here I have a 3D printed steel. There's a little bit of ferrite, a lot of porosity. And we can use the image quality map, just looking all the bad points. So very dark here. And that gives me, with highlighting, so there I link my data sets again. I go from 96%, 0.1% highlight, so about 3.9% could be pores. Now, this is something I don't really like to do because grain boundaries may also have very low IQ. So instead, I can go for a grain average IQ. So I remove all the dark lines at boundaries. And now you can see that the very poor image quality values is much less than what we had before. So I can do a highlighting again. Now it's 2.9% highlighted. So it gives me a cleaner definition. But still, with IQ, it's very sensitive also to polishing. You have to be a bit careful. So instead, we can use the confidence index. So here I take a filter, everything larger than 0.1. So I want to see the good points. There we go. And now you can recognize that the pores here are those white areas where the solutions were suppressed. And when I look at that, then the pore area here is estimated to be about 2.8%. Now, we can go a bit further than that, because once we have identified where the pores are, we can also look at those in more detail. So we can have these groups of points. And once we have that, we can tell the system, okay, group these together as if they are grains. And we call that anti-grains. So instead of just throwing these points away, we can actually quantify the pore size distribution. You can highlight that. So you just give a color coding on the chart. You can see the pore size distribution in my map. Small, blue, red is very large. And once you have that, you can do all kinds of geometrical morphology analysis also on the pores. So it's grain shape, aspect ratio, for example. Now, one of the more important things for EBSD is that we know where all the data comes from. So it's not just a single image, a big map, or a plot, but everything is linked together. And that is a very powerful correlation that we can use to select certain parts of the microstructure or really visualize things. So let me just show what I mean by that. Here I have a partially recrystallized steel again, and here I have my pole figures and inverse pole figure. And you can see here on the lower right in this IPF, get some black dots. These are actually the points that belong to the recrystallized grains. Those have very sharp, discrete orientations, and you can recognize those dots here as well. But the deformed grains are so bent that the clusters of points belonging to those grains just cover a very large part of the pole figures. Now, how can we visualize that? Because now we really can't see what's happening in those dark parts of the pole figure. So in this case, I just make a grain orientation spread map on top of my IQ. So we can see where the recrystallized grains are in blue. And then I can apply that color coding. Again, just right click, as I mentioned in the beginning. Then you have all the options you can use. And one of the options there is apply colors as highlight. So once I apply this color coding to a pole figure, I get this. So now you can see in green and yellow, even some red, those are the deformed grains. They're just spread out over the entire pole figure. And in blue, the recrystallized grains. And I can also identify those over the entire surface of my pole figure. So this is a very nice way to correlate the pole figures, inverse pole figures, with a map, so you can separate certain fractions visually. Now, here's another example of a feature correlation. It's a recrystallized film, and here I can look at elongation of grains. And what I would like to know here is the elongation of these grains parallel to a specific crystal direction. So is the crystallization going along a preferred direction or not? So this is a normal IPF map. That's the crystal direction sticking out of the sample towards us. So that doesn't show us any information about the elongation of those grains. So what we can do then is we can calculate the grain shape aspect ratio. We can show these very large or sometimes very small ellipses. And from these ellipses, we can identify the longest and shortest axis of the grain. And then we can quantify or identify the crystal direction parallel to the longest axis of the ellipse. And you can see that here in this image at the bottom. We call this a major axis IPF map. And now almost all the grains are orange to red, indicating that it's the C-axis that grows a bit faster than everything else. Now, one word of warning, be careful. It's in the plane of the sample. So any sectioning that you may do, cross-section, is very, very important, will affect what you see. Now, once you have that, we can quantify it in a chart. We can color code that. We can look at the growth direction of all the individual grains, and you can quantify that also in a different type, like a rows diagram. Now, we can go one step further. This is another material grain shape aspect ratio map. We can quantify that, but we can also compare that with the grain size. So here's the grain size map. In color coding, in black, you can just see the ellipses. There we have the grain size distribution. And we can then mix those two and plot them against each other. So you can see how the grain shape scales with another feature like the grain size. And this is available for many of the parameters that we can apply. Now, if you still need to do more, then we can also export all the information. So everything we do may be exported as plain text files. Again, just right click, and there's lots of options available to export data. And here I have an example of an aluminium kitchen foil. So this is just a piece of foil that you just have at home. Do an EBSD map on that. We can see those bands of different colors. We can look at the grain size distribution in there. And when I export a grain file, you have a lot of possibilities to measure and to analyze in more details. So in this case, I am just going to look at the number of neighboring grains for each grain, and you can see that you have a whole table with single grains, all their neighbors, misorientations with their neighbors, etc. So if you want to do your own calculations, this is a very nice way of getting your input data for that. And in this case, I'm just looking at the number of neighboring grains. This is just something I made in Excel, where you can just then highlight the distribution in this kitchen foil. Okay, now so far for the overall operation of OIM analysis with a number of examples and analysis capabilities that we have. Now, there are recently introduced 2 new features that I want to spend some time on. And one of them is parent grain reconstructions. The other one is what we call OIM matrix, which is based on dynamic pattern simulations. Now, the parent grain reconstruction helps you understanding and analyzing materials that have undergone a phase transformation. So for example, if you have a high temperature steel, then the microstructure will be austenitic. And when that cools down, single austenite grains can fall apart in lots of different ferrite grains. And the original austenite grain structure is lost because we just can't see it anymore. It's not stable at low temperatures. The other application that I want to talk about more is OIM matrix. We can use a dynamical diffraction theory to make simulations of EBSD patterns. It allows us to do dictionary indexing, and I will show some examples of that. And you also get really good quality simulations that you can use for polarity determination in crystals and do a lot more crystallographic analysis. I'm not going into those subjects today. So the parent grain reconstruction, we have a microstructure that we have measured. We don't know what the parent microstructure was at high temperature processing, but we can reconstruct it. And the software in OIM Analysis 8.6, we have implemented the approach proposed by Ranger et al. From 2018. So how does that work? Basic algorithm. We look at all the individual lamellae. In each lamella, in each orientation, we identify what all the possible parent grains are. And then we can look at neighboring grains, and we just compare these clusters of possible parents to see if there's one that they all share. Then that's most likely to be the parent that produced these child grains. Once we've done that, we can classify those as high confidence parents, which effectively means there's only one possibility, so we are quite sure that we know what the parent is. An ambiguous one, we have a few possibilities, not too bad, but we're not quite sure. And low confidence, there's too many possibilities to know for sure what's happening. And we can then apply an iterative approach. So first, we group the good ones together that we are confident that's okay. So all the blue ones are grouped together in single grains. Then we compare the ambiguous parents against these new neighbors, because that just limits the number of possibilities, and that grows into, they grow together. And once we have those larger initial austenite grains reconstructed, we can also recalculate these low confidence parents, because again, we have reduced the number of possibilities a lot, see if there are neighbors that they now match with, and just keep doing that, repeat that until we have identified the probable parent for all possible grains. And then in the end, you can do a little bit of a cleanup, but that's a choice you can make. So that allows you to go from a martensitic steel like this to that. And we can reconstruct this parent structure by the different orientation relationships. The most common ones are predefined, but you can also make your own if you want to. And we have verified this by comparing the same data set with different models, just to see what the variation in the different approaches is. And as you can see, they are all very, very similar. So we are quite confident that you get good quality reconstructions with the tool that we have implemented. Now, a few examples for that. One, this is a really old data set actually. It's a heating, in situ heating experiment where we can look at the low temperature to high temperature phase transformation. So going from hexagonal to cubic at around 420 degrees. When we do that, we capture some EBSD maps at different temperatures. So this is the structure at low temperature. So here we have mostly this hexagonal structure. At high temperature, we went through this phase transformation. You get the cubic structure. It's all yellow. That's indicated here by the yellow border around that pattern. Then we cool down. It goes back to the low temperature hexagonal structure again, etc. So we can just keep going up and down. And the special thing of this data set is that this microstructure is reversible. So it doesn't recrystallize for these temperatures, and it just flips from hexagonal to cubic and back again. And that makes it an ideal test case to see how good the parent grain reconstruction is. So when we look at that, this is as scanned. Here we have room temperature, which is mostly alpha with a little bit of retained beta. When we go to high temperature, it's mostly beta with a little bit of retained alpha. So what we do for the reconstruction, we take this data set, the ambient temperature data set, and then we reconstruct that. And this image here on the right is actually the calculated high temperature structure based on this ambient temperature measured structure. So when you compare the reconstructed one with the measured high temperature one, you see how very close that is, including most of the twinning and all the low angle boundaries we have in here are actually still preserved and reconstructed successfully from the low temperature structure. So that gives a lot of confidence in what we can do. Then another example, this is something I did very recently, and I'm going to shamelessly plug my blog that I wrote recently about this. Please take a look at the edaxblog.com if you want to learn a little bit more about this stud welding and the analysis we can do. And stud welding is a tool or a technique to connect a rod, a threaded rod, like from a bolt, for example, onto a substrate, put them together, get electrical arcing happening that heats up the interface. Then you get a melt pool here at the bottom, and then you just plunge the stud into this melt pool, let it cool down in a few milliseconds, and you have a very strong weld contact. That's the method for stud welding. It's very fast. It's milliseconds that all of this happens. And with EBSD, we can look in a lot of detail what is happening there. So here on the left, I have a large montage SCM image. There's 1800 fields. We can just make out a very large grained area here. That is what used to be molten. That's the melt pool that the stud plunged into. So the stud is here on the top and the substrate is here at the bottom. And when you look at the IQ map, you can see the changes that have happened during this stud welding. So here on right at the top, that's the original stud structure. I'm not going to talk about that, but close to the interface, we have this bright band. That's recrystallized austenite. Then we have this zone with these little swirls in dark. That is the area that was molten. And down here, we have the ferritic structure where the pattern quality, which was quite good initially, has deteriorated a lot. So what exactly is happening there? Just to illustrate that, I've just made a little drawing. Here we have a recrystallized austenite, the melt pool, and in this ferrite area we have two zones. One is fine-grained ferrite, and this is a columnar ferrite. Now, these are some of the maps. Here we can look at the small grain size. We can see those larger grains in the melt pool. And as you can see, most of that is green. That's austenite. And those darker swirls we have in here are ferritic. And when we then zoom in to an area close to the center of the weld contact, we can recognize the recrystallized austenite. And this is the melt pool. We have two layers of columnar grains. These are grown from both sides into the melt until those grains meet in the middle. And at the bottom, we have this columnar structure in ferrite, but that looks like lots of different grains instead of single ones. So if I just zoom into that, you can see that each column really consists of lots of different grains. And that suggests here that we had a phase transformation, that this actually formed as austenite that transformed into small ferrite grains with the different child orientations here at room temperature. And when we then apply the parent grain reconstruction, this is the original structure as measured, and after reconstructing it, we get this. And now you can see that the entire ferrite structure here at the bottom is perfectly continuous into this lower band in the former melt pool. And that means that this was part of the melt structure and that it actually crystallized in the austenitic structure and only later transformed back to ferrite. Now, why did that part go back to ferrite and not the rest? That's compositional. Here I have a map where we have this is the nickel chemical map collected at the same time as the EBSD map. We can see the elongated banded structure from the original stud. This is the melt. And here we have an area with lower nickel. And that's just incomplete mixing. What happened when the stud was pushed into the melt. And when we zoom into that, we can see exactly what happens. And the areas where we had low nickel actually transform into this ferrite, these red grains. And they're so small, that's why the pattern quality is much poorer than those nice large austenite grains. We index that, look here at the IPF map. And we have all those small blue grains everywhere. That's the ferritic structure. And when we do a phase parent grain reconstruction there, we get this. So now again, you can see that this structure really crystallized as austenite, and only after cooling, part of that fell back into the ferrite structure based on the composition. Okay, I'm running a little bit late, so I hope you'll bear with me. This is the last part of the talk on the dynamic pattern simulations in OIM matrix. And what we do there, we can generate simulated EBSD patterns. That tool has been implemented in the software, and it works by making a cloud of up to 2 billion electrons. You specify a crystal lattice, and you let those electrons travel from a center point outwards in all directions. And when you do that, you can get diffraction in all directions, so we know where the electrons are going. We can make that into a flat projection here by the Lambert projection. That is an EBSD pattern of an entire sphere. This is what we call a master pattern. So once we have calculated all the possible diffraction directions that we're getting, we get all these patterns. We can extract a pattern from a very specific orientation. And this orientation, you can be made to match your EBSD camera and microscope geometry. Now, just to illustrate that, this is an experimental pattern, this austenite. This is the dynamic simulation, just looking at the intensity coming out. And this would be a kinematic simulation that we have also used in the past. You can recognize the bands, but of course, this doesn't look very realistic. When we then apply a background here, we get a lot of detail that we can compare with the experimental pattern. And on the kinematic side, we can add more reflectors. Gets a little bit better, but still not good enough. Now, when we want to do a dictionary indexing, that means that we want to compare an experimental pattern against a simulated one. Now, how do we select what pattern is the same? What we've implemented here is a normalized dot product. So we just take a pattern, look at the individual lines in there, let's say, in the image, so not the bands, but just the columns and rows, compare that against the simulation and see what works best. But when you do that, we need to have a simulation. And for that, we need to identify what all the possible patterns are. And we can just say, okay, we need to simulate a pattern for all possible orientations, for all phases. And you need to do that at a given interval. But you have to be a bit careful, because if you want to do dictionary indexing this way, where you just look at 0.1 degree orientation changes, then for cubic, you're already talking about billions of simulated patterns that you have to compare every single pattern against. So you have to subdivide orientation space into specific units. So we do that, and we make a library with a sufficiently large interval between orientations that it's still manageable, and then we try to match the experimental pattern against all the possibilities until we find the best one. Now, just a quick chart showing this dictionary size that I just mentioned. Here on the horizontal axis, we have the angular resolution, and that indicates how many patterns we need to cover all possible orientations. And as you can see, the lower the symmetry, the more patterns you need. You have more possibilities. But already for cubic, 10,000 to 100,000, a million, 10 million, 100 million points. So if you want 0.25 degree resolution, we're talking about 100 million possibilities. And that's already one step further than here. But we are already at 200 million for triclinic. So that's not very practical. We can go coarse, and here's just an example of that. This is the original Huff-based indexing and two examples for dictionary indexing. When we take a 2.5 degree dictionary, the patterns are similar enough that we can identify all the orientations. We see a little bit of colored jumps here. Those are just the intervals of the simulated patterns. And if we go even coarser, you have 5 degrees, you can see then the patterns become too different, and in a lot of areas we start to fail in the indexing, and we can't really get a good result anymore. So 2 or 3 degree is the maximum spacing that we can get. So if you're interested in a texture or a grain size, that is probably a good value to use for dictionary indexing. 2.5 degrees will allow you to get good indexing results with a little bit of orientation jumps, but that's within the 2 degrees, let's say. You can get all the grain size and texture information that you need if you want to do the dictionary indexing. If you want to go smaller than that, we can refine. And instead of calculating these hundreds of millions of patterns, we can just look at the measurement based on a coarse dictionary, and then just calculate simulations just around that measured point. So instead of having it for entire orientation space, we are just doing a very small local orientation refinement based on the starting orientation we got from this coarse dictionary. And when you do that, you can get really nice refined solutions where we lose these jumps and we get a continuous color scale with, depending on how fine you want to refine, let's say 0.1, 0.2 degree orientation precision. This is quite computer intensive. What you can do to improve that is not index everything with dictionary indexing. So in many cases, we will have some points that index well. So what we do, we can again use the confidence index. We look at the original map, we find the correctly indexed points that have matching orientations, and then we make a filter to only select the bad points that don't belong to grains, it's just the noise that didn't index. Then we can apply the dictionary indexing only to those points and merge that with the initial measurements. So that way you can have the best of both worlds. You can use the very fast Hopf-based indexing for the initial work, and the points that happen to index, okay, we can use those. And then we have, you apply the dictionary indexing to the points that refuse to index, but we just couldn't find the bands properly, and then we can get a good indexing result for everything. So just to show that in a little bit more detail, here the original indexing, where we apply a CI filter of 0.1 again, is about 37% was correct. When we flip the filter, so only looking at the bad points, that's 63% of the total surface area, there we can do the dictionary indexing and then merge those results. And again, you get a good data set that you can use for most of the crystallographic and morphological analysis. Now then a final example. This is a picture from a data set that I got from Carsten Bonnekow at KIT in Germany. It's a extremely deformed compressed ferrite powder. And if you look here on the left, image quality is not so nice. We have those very small bright grains, those indexed, but everywhere where it's dark, as you can see here on the right, we just get noise. And when I then apply a CI filter, we still have about 50% indexing success rate, but there's a lot of area where we cannot get an indexing result. Now, we could try NPAR to improve the patterns, but on a material like this, there's a very big risk that the neighbor pattern is from a different orientation, from a different grain. And in many cases, that will actually degrade the indexing success rate. So that's not really an option for this material. So when we apply dictionary indexing to that, we get this. On the left, image quality. Well, image quality is based on the Hopf transform, so we can't use that for dictionary indexing. So this is like a correlation index where we can see how good things are. And already we have less dark areas than before. And if you look at the IPF map here, there's clearly less noise in the image. When I apply a CI filter, I went up from about 49% to 82%. So that's the original IPF Hopf-based indexing, and this is what I can get with the dictionary indexing of those extremely deformed, poor patterns. So just to summarize, I hope I've shown you that OIM Analysis 8.6 is a very, very powerful tool to investigate, visualize, quantify your microstructures. So everything you can do when you are looking at a question that is based on crystal orientations in some way in your materials, there's a very good probability that OIM analysis can help you to quantify that microstructure. So most of the basic maps and plots are directly available from the Quick Generate toolbars. And sometimes, okay, that may be enough, but in most cases, don't stop there. There is much more data to be had from your EBSD maps, and there are many, many more analysis functions available to really quantify and characterize your microstructure. When you need to do that more often, you can use templates. You can make your own one-button analysis tools. And on top of that, all the representations that we have, all the maps, plots, charts, etc., are linked to the points where the measurement was taken, and they can be correlated. Since the introduction of OIM Analysis 8, we have the re-indexing capabilities in there that have been developed more and more until what we have now in OIM Analysis 8.6, and that really maximizes the indexing success rates. So that is optimizing your image processing, the Huff transform, maybe the phase, but also dictionary indexing. So there's a lot of capability in there to even get good data out of materials that are really difficult to get good diffraction patterns from. And then with this last introduction in version 8.6 of the parent grain reconstructions and this OIM matrix with dictionary indexing, we just expand the capabilities a bit more. So with that, I would like to thank you very much for your attention. And if you have any questions, then please.
Hi, Renee. We have one question in the queue right now. What about the success rate of the parent grain reconstruction in the case of titanium alloys? Does the code work well for that? And what is the success rate in the case of child grains with low CI and with more unindexed points?
Well, first of all, the titanium. I have a number of titanium examples, but I just didn't have time to put everything in here. It works quite well, but it depends a little bit on the amount of deformation. If there has been a lot of deformation after phase transformation, then you would have to, widen the tolerances a little bit, and then you will see that you have individual lamella that may not fit anymore. But the overall alpha structure for titanium, the overall beta structure, the high temperature structure, can typically be identified quite nicely, including bending and deformation that already happened at high temperature. But that it really depends if you have a lot of low temperature deformation or not. If you have very poor quality indexing in the first place, then you have to be a bit careful. What you would need to do then is first try to maximize the indexing and the quality of your EBSD map before trying this. So what I would do is, first of all, make a CI filter where you just remove the bad points, see how bad it really is. Then you can try to re-index with the tools I've shown. If that is not an option, you can try to do a cleanup and just grow your grains a little bit, because the reconstruction is based on neighbors. So the grains have to touch each other. If they don't touch, we don't know the orientation, we cannot put them back together. So this is one place where you might want to use a cleanup to artificially grow your grains so they touch and you can do the reconstruction.
Renee, someone is asking for the price of an upgrade from version 8.0 to 8.6.
That is something that, as an application specialist, I'm always happy to refer to my colleagues from the sales group. And I can't give you an answer to that. It may change by country, by law, by taxes, etc. So I would really recommend to contact your local sales representative to get a quotation of an upgrade. And again, it depends on how many licenses it would be, how many you already have maybe, or what your existing version is on to 8.6. So please contact your local sales representative about that.
Okay, I don't see anything else coming in. So I think that's all we have time for today. Thank you, Renee. Great job. Thank you, everyone, for listening. Take care.